Hello everyone, my name is Tommy Pop. I have done my thesis in modeling of spatial variation in geotechnics. And I have been focusing on the study site to benchmark, namely Perniö test site. I will talk more about this in my thesis. In the current building codes, it's basically already stated that the variation of soils has to be accounted for. In today's practice, what we do with spatial variation is that we do go up with a drilling rig and take samples. And as soil is not just one value, you get many, right? And all these values can be characterized with, for instance, with a distribution. And in today's geotechnical practice in design, you have to pick one value. So what you do is you pick a characteristic value of this distribution and run one single analysis. And you often get one result, for instance, a factor of safety. But in reality, soil actually varies spatially. So you do get the distribution, and you also get some sort of signal, some sort of sign that it's softer and harder depending on location. And what you could do in a better approach is a stochastic simulation to get all these information into account. And you could basically run multiple simulations, and you could get multiple results, which would give you an estimate about the spread, the uncertainty of the result, depending on the spatial location of the parameters. So we're going to talk a bit. I'm going to go and talk a bit about spatial variations and signals. So you can see these two signals here. They have the same statistics, the same mean along the line, and the same spread, but they look completely different. So we need a new term, to describe the difference between these two. And I will talk about this right now for a little bit. So what you do is that you use something called the semivariogram, and you look at different distances. It's rather simple. You will look. So what you do is you take the measurements, and you take one location, then you take one step, and you take a new location, and you take these two values, compare them all over the measurement domain. And then you do this with one distance, and then you increase the distance again. So, for instance, for this short distance, you would get a value then, a correlation value. So if the values are the same, it's going to be lower on the axis, and if they're uncorrelated, it's going to be higher, depending on the distance. So you start with this distance, and then you increase the distance, and then you compare these values and the correlation between them, and you increase the distance until you reach, well, a maximum where there's no more measurements in between. And then you get these two variograms. So can you see which one is to corresponding signal? Well, it's pretty simple, because the left one corresponds to the bottom line, because the correlation, it's completely random. The randomness is continuous. So you can also see that in the signal that there's no, the signal is very uneven. It's very up and down depending on location, whilst the right one has some sort of correlation on lower distances, but tends to get more random if you look at more further away. So this distance here is called the correlation length and is denoted as theta. Well, and this term we can use to describe the signals in soils. So I have studied the site which is called Perniö test site, or test embankment in Finland, and it looks like this. So basically there's containers which has been filled with sand until the embankment failed. On the right you can see there's an excavated ditch to steer the failed direction, and in between the ditch and the embankment there's monitors. So there's inclinometers and basimeters and all sorts of instrumentation to document the failure. I have studied the cross-section in between, like in the center of the embankment. So as you can see here, the subsoil is typical for Scandinavia. It's soft soil, clays. Well, it's about 7 meters, and there's 2 boreholes. You can see the red lines here and there, 43 and 44, where soil samples were taken. Now, in the same cross-section, there was an earlier study by a Finnish scientist, and he wanted to study different soil models and their effects on the failure load of this load embankment up here. And what he did was that he compared all these different models. And you can see the line, the black dashed line, is the failure load. So you can see that we can begin with the left ones here. The limit equilibrium models underestimated the failure load. And it's typical for these simpler models because they just take in account of force equilibrium, but it also overpredicts. You can see there's the most right one. It also overpredicts the failure load. Now, if you look at the finite element techniques, which is all the rest with different soil models, there's still some variation. The interesting part about it is that these simpler, so to say, soil models like soft soil, which doesn't account for creep, does get the same results as the more advanced soil models. So it seems there's some more uncertainty to be accounted for. And I would suspect that it has to do with parameter variation. Now, when we look at failure load, we talk about ultimate limit state, right? When the embankment fails. So we would like to look at the parameters linked to that case, or those scenarios. So that's the critical parameters. Now, how does an embankment fail in stress space? Well, you have a stress in situ somewhere here, and then you load it, and then the stress goes somewhere in stress space till failure. Either it goes up to the Moore Coulomb line, which is defined by the friction, the effective friction angle, or it tends to go to the cap surface and then up there. And the cap surface is defined by the coefficient of lateral stress at rest, K0, which is also defined by the friction angle, this cap surface is going down till it intersects the mean effective stress, and this is the preconsolidation pressure. Now, the preconsolidation pressure is the pressure which the soil has, the largest pressure which the soil has ever been exposed for. It's like a student, right? It's like if you get pressure, then the more pressure you get, the tougher you get, so the more strength you have and the stronger you get in life. It's the same with soil. So the preconsolidation pressure can be defined in either pre-overburden pressure or over-consolidation ratio, OCR. The OCR is then simply the ratio between the pre-overburden pressure divided by the in-situ vertical stress. And what is important here is basically that a higher OCR gives a stronger, stronger soil, and it's more rigid, so it contains less water. So basically, it's stronger, but it's not as ductile as a soil with low OCR, which has lower strength, but is also more prone to deformations. Good. We have the parameters and everything for the research question. So my study has been like, how large are the uncertainties of the embankment to fail due to failure load, and what is the deformations due to the spatial variation of the pre-consolidation pressure? So I want to know the failure load and deformations. Good, let's go. Where's the method? Here it is. So the method used can be simplified in 4 steps. I will go deeper into this in the following slides, but I will describe them briefly. So first, we need to do a site investigation, and in these 2 boreholes, there are samples which was estimated for pre-consolidation pressure. These were transferred into OCR at this point. Then they were analyzed and interpolated using kriging interpolation, which gives you an estimate and a variance, which is basically, it gives you a spatial, a raster like this, where there is an estimate, a mean, depending on location, and you also get the uncertainty depending on location, the spread of the result. So with these 2 rasters, you can simulate multiple possible scenarios. I have done 1,000 rasters, and I'm putting them into a finite element mesh to compute the stability. And from these, we get the results. So beginning with the spatial variation and this, the site conditions, you can see that under the embankment, there is borehole 43, and the OCR is somewhat higher. It means that it's been exposed to a bit higher pressures. and its soil is slightly stiffer. On the side here, you can see it's more bright colors on the dots. That means that it's lighter values. But you also have a dot here which is a little bit higher. So there's some variation in the data. If you would take all these values, it's hard to find one characteristic value from all these values. So maybe we should do something else. So first we need to do is to check if the data. So all these data are summarized in here. So there's 17 values, and the mean is 1.3, and the standard deviation is 0.3. Now we can see that it looks like normal distribution, and that's one criteria for performing kriging interpolation. You can also see it by the QQ line. So this is basically the theoretical quantiles of a normal distribution divided by the OCR quantiles from the measurements. And if they were along the line perfectly, it would be perfectly normal distributed. Now it deviates a bit on the edges here, as you can see also in the picture up here. So if we do the same thing with the variogram as with the spots in this domain, we get this picture up here. This is basically to take all the arrows, not in just one direction no more, but in all directions. So you get all these dots here, and then you can bind them together to get these red dots here. And then you can see that there's a sort of trend of it goes up a bit, and then theoretically it would be random over here. That's my theoretical fit of the data. So what I did was I fitted this blue line to the red dots. And if you remember the theta, the correlation length, I estimated to about 2 meters. And then, since we take all the directions now, just up and down and left, we have two dimensions in my problem, right? X and Y. So we have to define the correlation length not only with just one direction, but also down. And the difference between this is called the degree of anisotropy, denoted side, and it's the difference, the ratio between the horizontal and vertical correlation length. Good. So when performing the interpolation, you could either assume that the variation is completely homogeneous. Like that means that the phi is equal to 1, and that the variation is the same in all directions. You can see this in the picture. You can also see that it's almost 2 meters where the measurement is influencing the value, and after 2 meters, the influenced by the variogram, the values tend to go to the global mean 1.3. You can also, this is the variation. So here's the opposite. Basically, at the point of the estimate, the variation is 0. We're more certain about the measurement value. And as you go further away, you get more uncertain. Now, there is another study performed on undrained shear strength on clay, where the anisotropy was studied, and the study concluded that there is a 10 times difference in the variation depending on direction. So you can see this in the image here, that there is a difference in variation in X and Y by the colors. Yeah.
I don't know who it is.
All right. For instance, this higher value here, you can see it's more certain that it's the same in this direction. It influences more than in the X or in Y direction.
It's a beautiful soundtrack.
You're recording it, so that's okay.
Yeah. All right. So, looking back at anisotropic fields, these two fields were used to compute the rasters. So I have an estimate of the OCR up here. It's higher, the darker colors, and lower here. And the uncertainty is from this raster over here. So it's both now by direction and also infused by anisotropic. So we compute different rasters for the analysis, basically. And I've done both the deterministic analysis and stochastic analysis. First, let's look at the deterministic analysis. So what I used was 3 cases, one with the estimate of the OCR, and one maximum and one minimum value of the OCR, plus and minus one standard deviation from the variance. And then I calculated 1,000 stochastic random fields. And this is one simulation. This is the one simulation of the stochastic raster. As you can see up here, it tends to go to a bit more darker colors. That means that the mean from the estimate raster here is influencing the results, and it kind of is a bit, lighter over here, and all the scatter is influenced by the variation. So these two types of calculations were run into a finite element analysis, and I wanted to study the failure load, and I also wanted to study displacements measured at 3 inclinometers along the possible failure line. This is the picture of the mesh, so I reinforced the mesh along the, closer to inclinometers and a potential failure surface. So let's look at displacement first. So from these 3 inclinometers, the deterministic analysis gave these results. What's interesting to see here is that you have the black lines, which are the measurements after the last load. So the load was loaded until to maximum load, which was at 28, but it didn't fail, so you had to wait for 2 hours before the embankment failed. So actually this was the maximum load, and then it just moved, and it was an undrained creek rupture after 2 hours. So all 3 possible scenarios gives a good estimate. Now let's have a look at the simulation of the random finite element mesh, and you can see there's even more lines, right? So there's quite a lot of this difference between the lowest and highest value, only due to the variation of preconsolidation pressure. And now Jelke has been waiting for this. I put them all into a nice picture like this, so you can see all of the simulation in one picture. So you can see that, it's turning color depending on how much it moves. And this field is the displacement in the x direction. So let's have a look at the failure load and the failure surface. So our theme analysis gave this. So it seems like it's failing like a nice convex shape like this. And the area of failure is normally distributed just roughly about 50 square meters. So there's not a big difference in how it fails. But the failure load then, the failure load was 87 kilopascal. So how did the deterministic analysis perform? Well, we can see that the estimate, overpredicts it a bit, but it's enclosed by the minimum and maximum value. So we're pretty close, right? What we did then, what I was doing is that I was running these stochastic simulations, and I wanted to compare the stochastic simulation to get the uncertainty of these results, because you can't really see how much the variation here differs. So looking at 100 simulations, it looks like this. So you can see the numbers up here. A lot of values, a lot of calculations resulted in a failure load of between 90 and 100, and you also had a little batch here between around 80 kilopascals. But you also had some 3 calculations at 100, as low as 72, and as high as 103. So after 250 simulations, the shapes look similar. I was expecting it to turn more normally distributed, but it sort of looks the same. There's still a lot of failures here and here, just more of them. And the numbers here are all, they're almost the same. So why does it look like this? Well, there are some discussions about that. It might be due to the raster influencing the results. As you know, the raster was not super fine, so depending on the resolution of the raster, it could influence. It could also be influenced by different failure modes, for instance, that it finds a shortcut into failing due to the variation of the preconsolidation pressure. So basically what you can see here is the cumulative distribution function, and it varies then from 0 to 1. And you can see that this is the failure load again. So it's very close to, well, around 50%. It's all in the range. Now, what's interesting to see, I want to really see the difference. What is the difference in the preconsolidation pressure between the lowest and the highest loads? I took both rasters to compare. So at the maximum, you can see they look almost the same. I was struggling, like why do we fail so differently? They look the same, but if you look really carefully, my hypothesis is that you can see right under here, it tends to be a darker colors, which means higher OCR, more stiff. And right here, it's not like that. It seems like it's actually really low values, about 1 to 1.2. So it seems like this location under the embankment is influencing how much the load the embankment can withhold. So I have now a good estimate of the uncertainty and why it is like that. And if you would like, you could also take a confidence interval, and you could say that the embankment is going to fail with, well, 20% certainty around 82 and 97 kPa, or yeah. So let's compare that to the earlier study, and you can see that there was a lot of colors already here, so I had to pick a new one. So it's in the range, and you can also see that all these models should also probably have the same uncertainty around them, but you can't really compare them like just one value like this. You need some sort of measurement on the uncertainty of parameters, and this is only due to the preconsolidation pressure. One parameter, there's many more. What's fun to see is that actually the median of the value is almost on the line, isn't it? So let's have some conclusions. Well, first of all, the method was proven successful in quantifying the uncertainties. So you could actually get an amount of, of certainty in the result, or variability in the design. And the uncertainty of, for instance, the failure load was estimated to be about 10%, only due to the preconsolidation pressure. And finally, well, there was the unmeasured location between the two boreholes, which was actually the most critical for the failure load. But there was no, samples taken there. So it really shows that it's important to take estimates at the right location. With that, I would like to thank and acknowledge some parts of these theses, especially Professor Jelke and Minna, which is here today, but also Dr. Lehtonen in Finland, which have provided me with much information about the site, and also my first professor in statistics in Vienna, Gregor Olaha, picture of him there, who introduced me to R and computations in statistics. And finally, the company Norconsult in Gothenburg, where I've been writing most of my thesis at. And they have also given me a nice input. Especially special thanks to Bernard and Dr. Jimmy. So that's all from me. Thank you very much.
It's time for some opposition. So how much time is open to me? It's yours. So about 15 minutes total, but at least some time for the audience.
Yeah, thanks for the presentation. and a crash course in statistics. It's been a while.
Great.
Statistics.
Yeah. The first thing I want to ask is how many samples would you say would be needed to get a somewhat accurate picture of a problem?
Yes, a lot. It depends. Like, there's two philosophies in this. If you would have for every site a lot of samples, or if it's enough to have like an empirical database of samples. For instance, in Gothenburg, maybe the anisotropy is the same, or the coefficient more or less, because that's the critical parameter in this analysis, the correlation length and also the degree of anisotropy. If there would be a sort of correlation between all sites in Sweden, then you wouldn't, and you could just get all these samples and you know an exact value, or at least a spread. Then maybe you don't need that many values. You could just pick a few and then use these parameters and run the analysis. In this study, it was 17 samples were used. It was shown that it was not enough to get accurate results of the variation. You could see, for instance, that standard deviation of red lines, which is, I'm a bit ashamed to show maybe, but you can see the red lines here, they're up here. So the line could be over here, it could also be up here, it could also be down there. It's only in the standard deviation. So it's not enough samples to draw accurate results, and there's a lot of biasness in the data due to this. How many is impossible to say, but as many as possible.
Okay. I also observed in your aims and objective that one of the things that bothers you is the isotropic nature of the soil and certain assumptions which are made in geotechnics. So I also observed in your report that there were assumptions which you also made.
Yeah.
The inputs of your data. If you wouldn't mind, I would ask which was the highest assumption which you made, and what was the influence on it on this research as well.
Okay, yeah. So one of the most critical assumptions in performing this type of analysis is stationarity, it's called. It's probably the easiest way to demonstrate stationarity is by these lines here. And to say that stationarity means that the mean and the variation is the same all over. So that the spread here is equally much over here as over here. Because when you compute a random field, then it's theoretical, right? It's not the actual data which is making the random field. So this blue line assumes already that there is the variation, and the mean is the same all over the domain. And that might not be true. There might actually be trends as well. For instance, if you wouldn't take OCR, preconsolidation pressure has higher values, as a function of depth. So that's a trend you would have to remove from the data. OCR is thankfully a bit easier to handle with because it's a ratio, so it's more normal distributed. So that's one assumption you have to assume, is data has to be normally distributed and also stationary. I don't know, it might be value, right between here, it might be some values which is completely different. You have to do that assumption that this entire domain here is the same population, has the same values, the same characteristics. And that's of course a bias in assumptions as well. As an engineer, you have to assume things like that. Well, that's it, I think, as assumptions goes.
I was thinking a bit about how big are the computational costs for this? Basically, how long does it take to make this kind of analysis?
Yeah, that's a good question. So well, a long time still. Even though in an era of better computers and more stronger computers and all this, it takes a long time. One analysis takes 2,000 seconds. I haven't computed that in minutes yet, but it's about 40. No, it takes about 40 minutes. I'm not sure about the seconds anymore. I changed a bit the criteria. So one analysis takes 40 minutes. And I also didn't use maybe the best way of computing. I use Plaxis and remote scripting Plaxis. And Plaxis, so basically what I did was all these raster things. I'm pretty sure, like I can explain. So what I did in Plaxis was that the algorithm I used was that it cuts out each piece one by one and sets a pair of material, a soil material in each. So it goes like tick, 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 tick. It's really slow and it takes a long time. And also Plaxis is not designed for these types of calculations. So it crashed after 900 boxes. That's why I just have 720. So don't try this at home. It was the method is maybe not the smartest, best way of performing these type of calculations.